Okay, so picking up from last time, we're going to talk a little bit about software frameworks. So you heard from Carl Henrik about some of the ideas behind probabilistic numerics, Bayesian optimization, and back to me now. And what we're going to do is I'll pick up from last time where we actually were talking about simulation systems. And the one thing I wanted to sort of get across about any simulation system, so we were talking about the need to emulate these complex simulations, is that very often they come to us in what we might think of as a monolithic form. So I think I must have zoomed out last time, didn't I? Need to zoom in again. Oh no. Where's that on here? Okay, we'll zoom out. Oh, that was 75%. 100%. So what we've got here is an example of such a system. So this is some of the most complex simulation we do at the moment, which is climate simulation. And we don't really have much choice apart from to simulate climate because we don't have multiple Earths that we can test things on. And the interesting thing about it is you speak to climate scientists, there's no individual that works on well, there are individuals who sort of pull them together, but most individuals are focused on one part of the model. So you might have models of the atmosphere, or models of the upper atmosphere and lower atmosphere, and how you work on these, the science that goes into these models is different. There might be chemistry there, or you also have models of the oceans. So in chemistry department, there's Luke Abrahams who works on, I think he works on atmospheric models, Peter Hayes in maths. Then there's, we've got people in the British Antarctic Survey that work on ocean models, particularly the flow of ice melting off ice caps into ocean models. And that turns out to be, we've got a video on this, one of my students was working with them on this, a big area of uncertainty. How much ice is flowing into the sea? We don't actually know how much will flow as temperatures go up. But there's these different components to the system. And roughly speaking, here I've just sort of chosen four that when we're trying to ask the question, what's going to be the future temperature? There's actually, there's the land model, there's an ocean model, there's atmospheric models, there's models of human activities, and people are stitching all of these things together. Now, what's interesting is if we look at the history of software systems, the way these codes were originally written, it's probably not monolithic in this sense, but if you certainly look within the codes, they're very monolithic. So a large code base, often written in Fortran or whatever the appropriate scientific programming language was at the time, of interacting code components. And one of the things I'm very interested in is if you can take aspects of computer science, what we think of, or what we refer to as a service-oriented architecture or microservices, or software as a service, and sort of apply them in these models. So actually more explicitly decompose into how these different parts are interacting. And you can do that at certain multiple levels. And the idea would be that you're really interested in experimenting with the system. So you want to understand, how does fresh water flowing into the Southern Ocean affect Southern Ocean currents, which in itself has some large effect on climate or whatever the relevant question is. I'm not a domain expert. And if you do your experiment, you do some analysis, and then you design a new experiment. And this loop just keeps going round and round. This is a real loop of science. We used to do this in Amazon, and we were constantly trying to speed up this loop because we sort of had this sort of idea. We don't know what science will want to do in 5 years' time, but we don't want slower experiments. We want more expensive, and we don't want more expensive experiments, and we don't want a narrower selection of experiments. And so when we were at Amazon, that was that underpins our pitch to the management about why we needed to do better science around simulation and emulation. So what did we want? Faster, cheaper, more diverse experiments, better ecosystems for experimentation. And the way we think you need to do that is through a bunch of things that we continue to work on now, things like data-oriented architectures, data maturity assessments, data readiness levels, that actually allowed us to get a better assessment of what the software in Amazon was doing. But coming back to the type of simulations we're interested in, there's such fun, this whole website on these packing problems, and it isn't isn't the world great that, you know, you can just get so deep into anything? And you're looking at the papers that prove these packing problems. It's like one person's written them and one person cited them. But this challenge we talked about before in simulation, and this notion of these packing problems, so packing 17 squares into what sort of size is the square? If each of those is a unit set square, what size is the square that they fit in? And it turns out that it's at least 4.675 times the smaller square. And this solution was found by a person called John Bidwell in 1997. From my memory, it's not a proven solution. That's just the best anyone could do. And look at it. You know, I'm sure there's some variation within that, but it's not like we can think, oh, I understand the underlying. I mean, at one level, we totally understand the underlying physics of what's going on here. But at another level, something complex starts happening while we start putting these systems together. Here's one where this is proven. So packing 10 squares gives you 3 plus 1 over square root of 2 is the square around it. So what about when these sort of questions of interest are sort of simple and we're just interested in that number? So maybe we're just interested in what the future temperature will be, or we're interested in just understanding how much fresh water is coming out of the Arctic rather than doing the whole simulation. And that's where emulation can come in. Well, as we'll see, we'll do a brief example. It can also come in nowadays on predicting the whole system through generative AI. But if we look at then this is the fun thing. So I took the Eric Friedman packing data and I created a data set out of it. And as we increase the number of boxes, then the size of the box that circumscribes them goes up in this really interesting way. And what I love about this is it looks like there's something going on there. I mean, I don't know what's going on there, but it kind of, you almost feel, I can't say, you almost feel like, oh, is that a little bit too low? Should that be smooth? I don't know. There's some kind of emergent process, right, that comes from this very, very simple system. And of course, this is simple enough to model in some way. There's not much point in about doing what I'm going to do next, but the point in emulation is that you then do a Gaussian process fit. And then instead of having to go through that whole simulation, you replace it with the Gaussian process. Now, what I think is already interesting is the quality of this Gaussian process fit isn't that good because the function doesn't deal with these discontinuities well. It's quite interesting this way that there's a sort of jump at each stage at some point, and somehow the function doesn't capture that. And in order to try and capture that, it increases the noise and doesn't interpolate well across the function. So once again, the sort of choice of your emulator can be critical. But coming back to, this is my re-rendering of as an SVG of something I found on the Met Office site, which is a sort of list of all their models. And if I remember well, I think orange is models that are in production. So this is UK Met Office, and gray is models that are retired. And what's interesting here is we start to see the granularity of these models. So this must be out of date because I think the latest model is less than a kilometer, or maybe that is the latest model, UK EP. But what's interesting is this is for a 48-hour forecast, and these UKV climate 100 years. So if they go Euro climate, the grid length, so when I say grid length, it sounds odd, doesn't it? But the length of the sides of the grid goes up. So you're looking at, some retired models here that it was working at a 300-kilometer grid length, and in 100 years. But look at the sort of the UKV climate here. It's forecasting out 100 years with looking at grid size, 20 years, sorry, looking at grid sizes of around about 3 kilometers. So that requires an enormous amount of compute. And as you go finer and finer a grain, that compute becomes a sort of problem. Now, I don't know all the details of this, but I think the Met Office in the UK is particularly keen on the fact that apparently the underlying physics is always run by the same code base. So they're just changing the granularity of these models. They're very proud of that. I'm not sure that's the sensible thing to do. I think it could well be that you want to change the physical approximations you use. I don't know. It might be the sensible thing to do. I'm not domain expert enough to know, right? But it just shows there's different choices for how you're doing these models. So although in some sense it's science and it's just Navier-Stokes equations, there's so many approximations that are having to be made, including when these models talk to each other. the way they pass energies and masses and all these sort of things to each other. You need to do a whole load of collaboration on that just to make the model give sensible results. So the sort of vision is that when you think about emulation, that what you've got going on here is some combination of these different things, some combination of potentially different simulators. So, and here the size of the box is supposed to be how fine-grained the simulator is. The larger the box, the more compute, the more fine-grained the simulator. And you're trying to tally it back to what's going on in the real world, the ultimate answer. But the problem, of course, in climate being that we just have to wait that out. We don't know what's going to happen. We can guess. So we can't really afford to wait that out. And so where statistical emulation comes in is that we can take some question or quantity of interest. For example, the thing we were trying to do, and you know, this isn't applied in practice with the with British Antarctic Survey, was do some emulation of the ice sheet melting, because it's very computationally intensive to get it accurate. You have to go down to very small grid sizes to model the flow of ice over valleys, right? And the models they have were just too slow. So we were trying to support that with emulation, but actually all we found out is you had to keep going finer and finer grained. Currently the uncertainties well, my last understanding of it, we couldn't resolve those uncertainties. We couldn't go fine-grained enough to find out ground truth. So we couldn't build a simulator big enough to capture what we felt was going on in the real world. And I should say, you know, I'm peripheral on the project, so I may have misunderstood that a bit, but that's my best understanding. But what we would like to do is create a world in that project where we have different fidelities of simulation. So actually, there's parts of the Antarctic where the ice is sitting on plains and then it melts in very predictable ways, right? So ice sheets over Cambridge would be very easy to model. But ice sheets over the Alps, extremely difficult to model because of the interactions. And that's what's going on in the Antarctic, an enormous continent which has mountain ranges and plains. And so you might want to sort of say, well, in these regions of high fidelity, we do some high fidelity modeling. In these regions of low fidelity, we do some low fidelity modeling. And that leads to this idea that we're going to talk about at some point. Well, first of all, trying it back to the real world, the actual data, but also having models that can cover different fidelities. So models that are adjudicating between the high fidelity and the low fidelity situation and combining the information together to present something that hopefully calibrates back to the real world. And because these models are designed with a particular question in mind, with a particular data set in mind, it's always been my thought, although we'll see, you know, a different approach that's coming from Gen AI at some point in the lecture or maybe next lecture, that you're going to need multiple different emulators according to different questions. So the thing that always fascinated me is actually what you really want is to understand how these simulators are pieced together such that you can deploy emulators on the fly to answer the particular question you're interested in that week, where each of these things is potentially just a some Gaussian process or whatever, trying to relate trying to take the simulator, understand where the simulator is good and where it's bad and where the simulator is valid by tallying it back to the real world. So one of the things in Amazon is often that these models were also different types of models. They weren't even sometimes simulations. Sometimes we were dealing with a world where there was some optimization going on. There was some complex machine learning model. There was some operational research model. For example, what's called the news vendor problem, which is the problem that Amazon solves to work out stock levels. So they try and work out the demand and the supply of every product. And then they solve that using something called the news vendor problem, which is like the abstraction is someone selling newspapers. How many newspapers do they order? Well, it depends. The assumption being that the order will be, what they'll get is exactly what they order. So there won't be any variation in supply, and that the demand is some distribution function over demand. And they know their profit and they know their costs. And then the news vendor problem gives you an analytic solution in terms of the profit and costs about what point on the cumulative density function you should operate at, whose form is very simple, but I don't recall for the moment. So it sort of says, well, like you need to operate at the 90th percentile of your demand, given this cost and these and this profit. So that sort of model was operating underneath things to decide how much stock Amazon ordered. But then if you wanted to do some sort of downstream analysis of what was going on, some sensitivity analysis, then what was going on there is they had an approach called bridging. So bridging in econometrics, and I don't know if this is universal outside Amazon, but they would use this term all the time, would be applying linear models, just linear models to the operating points of these different simulations, which were in fact software systems that were driving the decision, but you can see them as a simulation. And then looking at the operating point of those linear models and using that operating point, linearizing around the operating point to explain why you were over or under stock against expectations. But the fascinating thing was, if it was a question people had asked before, so if the vice president had asked this question lots of times in the past, we could do it very, very rapidly. But if it was a new question involving different parts of the ecosystem, it would take like 8 months to just get the linear model into the code, because the code was, code's functioning, but it's not been designed in this big picture way to allow someone from the outside to come in and say, I want to plug in here, here, and here and build a linear model, right? That's not how the software engineers built it. And that's similar to the climate stuff. You get the same thing. You get these architectures that aren't built with this process in mind. So we're going to briefly sort of mention GPy, which is a Gaussian process software package that, let's see, it would be about 14 years ago, started building this, and it's still quite widely used. It's still maintained on the Sheffield ML site. So it started in working on this in about, probably about 2011, 12 maybe. And there's a sort of community. Of course, it could always be more active around it, but the software is sort of working and usable, and it tries to make it easier for you to apply Gaussian processes. So it sort of looks a bit like this. Where you want to use a particular covariance function, we tried to create a user interface, which I think, by the way, is now standard. We were the first people to sort of do it like this, but I think most of the packages have followed what we did. We were the first widespread Python package, but we also predated JAX and PyTorch and TensorFlow. They didn't exist when we did this. So people have more recently have done GPyTorch and what's the TensorFlow? GPFlow, which same type of idea, but as is sitting on top of NumPy. But very important to us when building, I'm not sure if the others put so much attention on this. I haven't used them widely enough to know, but they're all, you can use any one you like. To be very clear, the Emukit package we'll introduce at the end allows you to do whatever you like. Use any Gaussian process package you like. It's a very clear coding form so that you can actually see what's going on. So here you're creating a RBF or an exponentially quadratic kernel in the code. And you can there's a selection of covariance functions given that you can choose between, or you can define new covariance functions. So remember, the properties of the Gaussian process are defined to the covariance function. So we implemented a bunch of those. I mean, back in those days, we were actually implementing, believe it or not, all the gradients by hand. Their own gradient implementations as well, because we didn't have these autograd techniques widely available at that time. So you end up being able to do things like this. So the top two have gone off the screen here, but the basic idea is to show you can do things like combine a covariance function of an RBF with a Matern 5.2 very quickly to do this sort of thing. And that is exactly, so it's funny, let's see if we can, so I'm going to try and call something up, because I just saw this morning and I didn't realize it had gone that far. But remember, I think I spoke about so I think I spoke about this as something that we use the multi-fidelity. Can I get over it? Where is it going to come? Or maybe I'll just go like that. I'm here. Oh, why is that not? Control. Oh, there we go. This is the Mark 30 drone that I just saw some videos off TikTok of it delivering in practice. So this is it's similar to the drone that we worked on. It's missing the cowlings that were protective around here, but reduced weight, because the cowlings weren't part of the aerodynamics. It's just these two surfaces. So it's an evolved drone that is now, I think, approved to do drone delivery. Look, here's an actual reporter behind the scenes. Yeah, that was actually the facility we used to go in and do the testing. So it used to be top secret, but now apparently they put pictures of it on the web. So this drone here, the people that worked out how to do this control, they used GPI. And they used GPI by working with us and understanding what these covariance functions were. And then once they'd understood that and how to pull these things together in the sort of way that allowed them to do the control that captured the way the aircraft was performing, they shipped code into production. So using these frameworks through emulation. Here's another example where you can do multiplication between covariance functions. So it's just a way of trying to make it very easy for you to sort of pull these sort of things together. I suppose compared to the way deep neural networks are done nowadays, it's not very impressive. But back about 15 years ago, it was quite state of the art. And as I say, there's lots of other packages that are more recent, but GPI is still maintained. And this is actually Nicolas Durand giving a talk on kernel design in 2016. So this would be 1 or 2 years before Amazon came, but there will be Formula One teams in the audience and talking about how you create the sort of interesting functions, how you bring in your knowledge and your understanding into the covariance function so that you don't get those problems we saw in the package design where the noise is too large and it's not capturing the discrete jumps or whatever the relevant problems in the system of interest is. Okay, so here's a sort of quick Gaussian process regression example. All these are in the, there's no obligatory worksheet today, but you can follow through all these examples of GPI in the worksheet today. So here's a sort of a data set, and here's a fit to the data set that assumes quite high noise, and here's a fit that assumes quite low noise. So the interesting thing is you get this with Gaussian processes, that there's actually two optima here. These are, from the model's perspective, if you initialize it in one place, you will get a solution that looks like this, where it's assuming that this is not signal, it's noise. And that's a local minima. The global minima, or presume this is the global minima, there's only 3 or 4 parameters, so sometimes we do grid searches, is this one where it's assuming actually there's very little noise from this covariance function. So that's something always to be careful for. Always check what your noise level is, if your noise and what your signal to noise level is something reasonable. In this case, your signal to noise level is there's virtually no signal, it's all noise. Here's got a very high signal to noise level, and you can check that with the covariance function parameters. So you just look at the variance scale on the signal piece, which would be your kernel, your RBF, or your Matern 5.2, and then look at the variance scale on the noisy bit, the thing that's the Gaussian noise, which in this case would be virtually 0, right? Because it's a sinusoid, so it's interpolated and there's no noise being added. So the sort of thing you can then do is you can also do things like fitting to complex functions and then doing sensitivity analysis. So there's another example in the GPI introduction that sort of shows that. And then this leads to, I guess, what is the core idea behind this course, that all of these notions can be used within the domain of uncertainty quantification and design of experiments. And this is a domain that goes well back before machine learners started getting their grubby little hands on it. So here's this paper from 1979, and they review their different forms of sampling for experiments. So what do we mean by an experiment in this case? Well, an experiment in this case is running the simulator at certain values. So I've got a simulator. My experiment is going to take the form of running it in certain positions and then fitting my Gaussian process model to it. And by doing that, I can do sensitivity analysis, for example, on the simulator, because the sort of thing I can then do is I can say, well, across these 10 values, how is, for example, the future global temperature in 100 years' time, how is it varying as I change the amount of sort of fresh water that's entering the Southern Ocean across the range of values, which I think might be appropriate. And that's a sort of form of sensitivity analysis that allows you to sort of decide, do I need to focus on that, or do I need to focus on some model of current drift, which also might lead to one of these tipping points? Well, the way you try and tell is you design your experiment. So you set a selection of points where you're going to run your climate model, and through those points, you then fit your Gaussian process to it. And then you do the sensitivity analysis on the Gaussian process. And you hope that that's going to roughly capture what the sensitivity analysis would be on the full climate model. The reason you don't do the full climate model is like each data point on the climate model probably takes 6 or 7 hours to run, whereas each data point on the Gaussian process takes 6 or 7 milliseconds, or maybe a bit longer, who knows, to run. So that's the sort of idea of emulation. But how do you get the points? And this is what this paper reviews, is a sort of set of approaches for getting the points. So random sampling, so sorry, that should be in the notes, not the slides. It's popped up here, is where that's just where you just, across the domain of interest, you just take points randomly from the domain of interest. But then there are other sort of approaches, so which aim to do a better job at covering the space, making sure that you're getting points in the space. Now, when you think about this, when Carl-Henrik was talking about probabilistic numerics, right, that is also a design of experiments situation. So how wide are those bins? What should you use to interpolate across those bins in order to get the integral right? Now, these sampling approaches are actually, in some sense, akin to the simplest form of integration, where you just do Monte Carlo. You just sample from the input domain, right? And then you use that sample from the input domain to try and make the prediction. But we've got this intermediate step where we're going to fit a Gaussian process to that sample from the input domain. And in order to get that fit right, there's certain things that sometimes you might do. So if you do a random sample, it's quite likely that there'll be some space with no data points in it. So these stratified, and the very popular one, the Latin hypercube sampling, they're very popular for ensuring that the points are spread out in a sort of way across the space of interest to make sure that you can get a representative function fit. So that's the kind of classic approach. Now, and that's also the approach that you're going to, when you do your fits, start with. So you do your design, you're gonna, when you do your projects, you've got some simulation you're interested, some question you're interested in, you'll need to do an initial Gaussian process fit, and you'll typically select one of these methods. And most of the time, you'd probably select Latin hypercube sampling in order to get the coverage. And then what you saw in the Bayesian optimization and the Bayesian quadrature was active sampling. Given that, where should I choose the next point? Where am I missing information? Given what I'm seeing in this system, where do I go next to try and get an intelligent sample from the system? But your starting point is to use these design of experiments approaches. Oh, again, apologies here. I've got this a little bit off the thing. Now, I just wanted to sort of make a side comment, because we've been sort of talking about this for sort of 5 years, something like that. Doing this course for 5 years, really within the knowledge that this interface between the physical world and machine learning is just one of the most interesting interfaces. We happen to have gone down this route of doing emulation, surrogate modeling, focused on Gaussian process, seemed the most sensible thing at the time. But then just to try and get you in the mood for, let's see, oh, I've done that on the wrong thing here. Let's see if I can, copy link. This is new for this year, which is why the slide is a bit messed up. So this is this idea taken to the extreme, right? 5 years ago, this wasn't imaginable when we started this course. But this is the sort of this is the most accurate model of weather across the world. And the extraordinary thing about it is it's not coming from simulation, it's coming from emulation. So with generative AI, what we're talking about here in terms of emulation is, oh, well, you want to know the temperature, you want some sort of uncertainty or whatever else. But in this domain, because people are running weather simulations the whole time, there's an extraordinary amount of data. The problem you'll face in many domains, I kind of loop that. The problem you'll face in many domains is that we just don't have the level of data required to build the sort of foundation model that we would need. I mean, I think Hadi's going to give us a guest lecture on how we're doing that across wider science. But in this case, DeepMind got together with the Met Office, I think, can't remember who their partners were, and trained on, this data is being produced every day, right, at fine resolution. And all of a sudden, it means instead of running that weather model I was showing you before, you run this thing they call GraphCast. And you're getting the most, I can't remember under what measures, but at 10-day forecast, this is the most accurate forecast. And this is incredibly important. So I've got a colleague in Shira, who I may have mentioned in previous things, in Kenya, who is now combining GraphCast predictions with local weather measurements to get a far more accurate forecast in Kenya. And you think what this means agriculturally, that when it's going to rain. I don't know. I've kind of, if this was my real YouTube account, you'd just see a load of farming videos. I'm like quite into farming videos. But one of the interesting things, farmers going around fixing things, I don't know. Could be worse. So one of the things that I find, it is sort of it's got car videos down the side at the moment and my lectures. I'm not sure which account. It's the Open Data Science one. So I really do like watching farming videos. And one of the things that's fascinating is so much of what they're doing is dependent on their ability to predict the weather. So the farmers will say, well, I'm drilling today because I know it's going to rain tomorrow and I need the rain to sort of come in and the grain to grow. Or another interesting one is they do this technique of, if you don't plow, what you do is you allow the weeds to grow and then you spray them off. But if it's going to rain the day after you spray them off, that doesn't kill the weeds. So you want a gap in the weather. You need a bit of rain. So what you do is you take out the old crop, you do some sort of thing that triggers the weeds to grow. Then you hope it rains the next day. And then you wait like a week and the weeds just come through there at their most vulnerable. And then you spray them off with the minimum amount of pesticide. And then you plant your crop, right? So how dependent is this on accurate weather predictions? And of course, they have extraordinary weather predictions because they're in the UK. These things are being resolved 1.5 kilometers. Well, these farmers aren't going to die if they make these decisions incorrectly. But, and maybe the ones in Kenya aren't either, or Uganda. But it's got the same set of problems. It's much more sensitive to these issues. But then also really interesting things like cultural problems. Like we were talking to a colleague there who was a scientist, but he's back on his farm in Uganda. And he said, well, actually, I have to be quite careful about how much I pay attention to the weather forecast, because if it's not being used locally and I'm doing something different to other people and that thing works out, there'll be suspicion. Because there's a lot of interesting cultural ideas around, like I caused it to rain, right? Which can emerge if this is a repeated pattern. So the key thing is also you need to educate people in the use. But so using this GraphCast, I mean, that's just a transformational thing for the quality of weather predictions, potentially. I don't think it's well verified in these, because there's less data in Africa. So maybe it's not performing that well in Africa, right? In Kenya, this would be, this area. Yeah, right. It is where a lot of my friends are based. So really exciting, and totally, by the way, nothing really to do with the way that we're talking about emulation or we're talking about it 5 years' time. But actually outside the computational budgets of most groups. And I hope Hadi will give us a sense about what it looks like, because they are working on it for cosmology and this sort of thing, the equivalent models, right? Which is a very, very exciting thing of Gen AI being used in this way. So it's building on simulations rather than on human data, right? But that isn't kind of what we're teaching you to do, partially because when 5 years ago, this just wasn't possible. And secondly, because actually the amount of, there aren't that many things you can take out in this way, because there aren't that many things with that much data that are so obvious that everyone needs the answer. We can't all afford to spend 15 million or whatever the cost was to answer our question. If we could afford to that, we probably wouldn't need to be looking at emulation as a substitute anyway. So there's still many, many scientific problems where these smaller emulators are much more useful. And indeed, Google themselves optimize their data centers using Gaussian processes for Bayesian optimization, as they recently revealed. So it's not as often talked about, but it's extremely commonly done. So we sort of had, while we were at Amazon, we did a number of software projects to try and support teaching vice presidents and managers about emulation and how it could be useful for improving the supply chain. And this is one project that was Leah Hurst and Cliff McCullum, which I still like, because it was a sort of, Leah was a software engineering intern, and she came in and built what we call the Emukit playground, which is our attempt to explain what's going on to managers. So it's all sort of like JavaScript, taxis based, trying to sort of show to managers how, oh, look, if you put more cars on the road, you won't, what will your profit be? So it's just a simulation of a very, we had this sort of thing that at the time, it wasn't public how Amazon's purchasing system was working, and we weren't sure we were allowed to make it public. So we kept using Uber examples for our public demonstrations of the system because we weren't Uber. But nowadays, as one of the examples you've been given, there's Scott Mini, which is a simplification of the Amazon supply chain. So we could have done it on Scott Mini nowadays. But so that's the Emukit playground. But what it's actually surfacing, and this fellow here is a young and enthusiastic software engineer who worked with me at Amazon, and since then now he's just graduated from his PhD, working on not directly related stuff, but he has a lot of side projects on optimization. But Javier Gonzalez was the project lead, and Mark Pullen came to us from Ferrari, and he did a lot of the work on the Prime Air stuff. Getting that working. So because he'd done similar work at Ferrari. And then after he left us, he went to another engineering company doing this sort of stuff. We brought him in specifically because of his expertise in this type of thing. And Marin, who is a machine learning engineer, built Emukit. And Emukit was our attempt, and I'm sure, again, if we were to build it today, one might build it differently, to build the most flexible, functional, usable set of software for allowing you to do a range of these things, Bayesian optimization, sensitivity analysis, using different emulators underneath, whether they're Gaussian processes or not. And you'll see under here a set of examples. And in effect, what I'll do for the next couple of lectures is just go through some of those examples. We're going to look at, you've already seen Bayesian optimization. Carl Henrich's lecture isn't based on this, but my lectures will be based on the sensitivity analysis here in multi-fidelity emulation that are just sort of online with examples of how you do these things in practice. So yeah, that was the team, and there's actually a paper around it. And I should say, yeah, that all these. So Henry Moss, he was an intern with us. He's now a fellow in maths. Continues to work on related things. So a number of these people were interns who came and joined it. I was management. Yeah. There's a paper on it somewhere. But basically, in the sort of final few minutes, what the theory is that, and that should say it's not GP mod, it's GPy model. Oh, I can't scroll. Oh, there it is. GPy model wrapper, right? So as I say, it's very flexible because it's trying not to say, oh, you have to use our Gaussian process software. It's trying to say, you can use whatever software you like. So in Emukit, the notion of a model is some kind of emulator, right? And in this case, this one is a GPy model wrapper. I wonder if that link still works. I didn't double check it. Let's see. Here's a notebook that is, if you've got your own model that you want to use, this notebook describes how to integrate your model. So in this case, the notebook's explaining how to integrate the scikit-learn Gaussian process as an emulator. And you basically end up defining a class that inherits from the model interface. and then you can use that as the emulator, right? So that's it's a very modular package in that way. Now, can I get back? So that's the notion of a model in Emukit. And then the structure is you have a loop, which is going around, it's going to do the outside to which point you get next. You're starting with some data that you've got from design of experiments. That's coming in, you do your model fit, and then you're going to go around and loop with your model, doing a candidate point calculator. The acquisition, you've got to define an acquisition function. So that could be the one for Bayesian optimization, but it might be one that's not Bayesian optimization. It might be quadrature or something else. And then you have to do your acquisition function optimize. You remember the acquisition function that Carl-Henrik was talking about, which for some bizarre reason we maximize, even though the tradition is minimized in optimization. And then you have your user function, which is the one that you're trying to simulate, right? So that's coming from the simulator. What's the function I'm trying to emulate? Is it climate? Is it something else? And then there's a model updater, right? Because you've acquired this new point, you have to integrate it in your model, do some extra learning, and then you go around the cycle again. And then finally, a stopping condition. When do you want to stop? When have you had enough? When you're happy with the results you've got? So the Emukit vision was basically, and it has got a community around it. I think it hasn't got quite what we really would like to see is this. We have these models with the model interfaces going into the Emukit methods. And then what we really would have liked, and we didn't quite see emerging, was a notion of a task, where the task is something you're actually trying to do that is a bit larger than the individual loops. It's like perhaps optimizing, getting the best neural network. And so we'd wanted people to define tasks, but that didn't quite work out. There's some tasks defined by us. But so the different methods are Bayesian optimization, experimental design, et cetera, et cetera. Oh yeah, I sort of described this. I've effectively said all that. It's there for reference and also in the note. And then, so there's an Emukit tutorial. And under the Emukit tutorial, we all use, so for different ones, which include the multi-fidelity emulation, we're going to go through that. We'll not go through Bayesian optimization because Carl-Henrik's already done that. We'll do sensitivity analysis and experimental design in one lecture together. That will be next lecture. And then the whole thing sits on the model-free design of experiments, which is that first step where we just call on this code that someone else has written for the Latin hypercube and whatever else, right? So these are the sort of different components. The hope is that those components can come together in a pleasant way. So I just in the last few minutes, so you've seen a lot of this function that's actually called the Forrester function. So I just wanted to introduce you to Alex Forrester because I got to meet him once. Oh, how did that go so quickly? Oh, it was already playing. How's that not playing? Oh, right, like that. That doesn't seem to have helped. Here we go. Oh, here we go. Oh, that's weird. Okay, well, it's trying to show some of Alex's work. So Alex comes to this domain from design engineering. And what he's got in this case is, maybe we'll just go to YouTube. And maybe that will work. That's weird, isn't it? You play. It's almost like it's, oh. So here's something out of my keyboard. Anyway, it will play from the, there's clearly something slightly odd going on with my YouTube at the moment, which I've never seen before. Just going right to the end very quickly. But it's a brace stroke kinematic simulation. So Alex works a lot I think he's in mechanical engineering or aerospace engineering in Southampton, or he certainly was last I checked. And he's been doing this sort of design through emulation for sort of a number of years. And he's the person behind the Forrester function. So he defined this function. He created this function. So it's the Forrester function, right? And it's the one that you've been using for Bayesian optimization, but we can also use it for sort of experimental design. So if we get an initial design from our design of experiments that looks like that, and we're trying to fit Gaussian processes to it. So I've tried to show you the sense of the error bars here. What we then want to do is choose an acquisition function. Now, a very common acquisition function. So you've looked at so far the Bayesian optimization. And in Bayesian optimization, you're interested in finding the minimum. But it might be that you want to understand the whole function. And certainly for sensitivity analysis, you want to understand the whole function. So what might be a good acquisition function for trying to understand the whole function? Anyone? It popped up briefly. But what might we choose? Where might we want to choose the next point? Highest uncertainty, yeah. I think you were going to say the same thing. Yeah, highest uncertainty seems very sensible. And that's what uncertainty sampling says, is that you just choose according to the highest uncertainty. So that's the acquisition function under uncertainty sampling. So what we do, though, is in practice, it turns out to have a problem. And there's an alternative, which is called integrated variance reduction. And we'll come back to the point when we do this sort of example in practice, and we'll see who can sort of spot what the problem is. So this is the acquisition function for that first point under pink is uncertainty sampling. And remember, high is good. And green is integrated variance reduction. So integrated variance reduction, I should say, the difference between the two is integrated variance reduction is trying to find the point that minimizes the sum of the variances across the whole thing, the integrated variance. Whereas uncertainty sampling is just trying to choose the point which is associated with the highest variance. So they're different, which might not be surprising. The green integrated variance reduction has this sort of interesting, where you see these green points is where the original data is. So it's like, you really don't choose. They both don't choose there, but the integrated variance reduction is really don't choose it there. But why, where is it different and why? So it's actually, where does integrated variance reduction tell us to choose the point? Where's the green line highest? 0.4, yeah. And where does uncertainty sampling tell us to choose the point?
Or 0 now.
Well, no, 0.4 is good, but also it's also at 0, yeah. What's going on there? You can go back and look at the fit. Because of course the error bars at 0 go large, yeah. Because you're very uncertain, and if you will get that is a maximum uncertainty point. So choose there, sure. Apart from the integrated variance reduction is shifted; it's on one side only. So because you're only integrating from 0 to 1, you care about the function in that regime. The integrated variance reduction actually compensates for that. So you see that there. And so if you do the uncertainty sampling, you get this problem where you sample at 0 and then you choose a point there, right? Or you can do, because it's from an uncertainty sampling point of view, it seems like a good idea. It of course goes away. Here's the acquisition function after that. Then it goes to 0.4 and eventually you get there. But the integrated variance reduction won't do that. And we'll look again at that next time. And I'll just check. Are there any questions from this time on what we're doing so far? So we've